Our first example is a tower from the top of which a student throws a stone straight up. It goes up and comes down and hits the ground. Sketch the velocity versus time graph. Let us start by taking upward direction as positive. So the initial velocity is at time t equal to 0, a positive number, and the acceleration due to gravity is a negative number because it points downwards. Now the entire motion is one of constant acceleration. While it is going up, it's accelerating down. At the highest point, when the velocity is momentarily 0, it is still accelerating down because the force of gravity has not stopped acting. And while it's coming down, the acceleration is downwards. Now the acceleration is the slope of the velocity versus time graph. So the slope in this example is a constant negative number equal to minus g. So the graph for the entire motion will be a straight line of negative slope. So let's draw that. So the velocity starts at some positive number and decreases as it goes up and reaches a velocity of 0 at the highest point and continues on with the same slope. Now the velocity has become negative and it becomes more and more negative, larger and larger in magnitude, and this is what the graph looks like for the entire motion. And this is the point in time when it has reached the highest point, when the velocity of the stone is 0. That is the time when it reaches this point. After that, the velocity is more and more and more negative until it hits the ground. So this is the v versus t graph. Let's go to the next example. So in this example, we have a long box and there is a ball inside. There is no gravity. The ball starts at the leftmost wall, moving with a constant velocity until it hits the right wall, at which point it suffers a completely elastic collision, which means it bounces back with the same speed but going in the opposite direction. So this way it keeps bouncing back and forth. So the time it takes to go from one wall to the other is going to be the length of the box divided by the speed, which is the magnitude of the velocity. So this is the time t. So how do we draw the velocity versus time graph for this problem? Very good. At time t equal to 0, it's at the left end, moving with a velocity to the right, and let's take the positive direction to the right. So the velocity is constant for t seconds from 0 to t. The velocity is constant. At this point, it suffers a collision and the velocity gets reversed. It becomes exactly minus of this value. So for the next t seconds, it's constant at a negative value. So this is again, at this point, again the velocity reverses itself and remains constant for t seconds, and then again for t seconds. So this is the graph, velocity versus time. If you like, you can join this discontinuity with a dotted line, like so. You need not, but if you like, you can do this. So basically, the velocity versus time graph is a series of horizontal lines for this problem. Let's move to the next problem. In this example, a ball is dropped from a height h. It starts with initial velocity 0 at time t equal to 0. Now as it moves down, it goes faster, 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 accelerating with g. And when it hits the floor, we are going to assume it's an elastic collision, and so the velocity gets reversed. And then as it goes up, it slows down until it reaches the same height. It reaches the same height because there is no loss of energy. We are going to assume again there is no air friction, and it keeps bouncing up and down forever. Plot the velocity versus time graph. Let's quickly look at this. If you have u equal to 0, and since the acceleration is g, and I'm going to take up as positive again. Let's first find out how long it takes to hit the ground. So the displacement is minus h, the height through which it falls, minus because it's downward and I've taken up as positive, is equal to ut, u is 0, plus half at squared. The acceleration is minus g, t squared. So we get straight away t is equal to square root of 2h by g. That's the time it takes to come down, and it will take the same time to go back up. So on the time axis, let me first mark off t, 2t, 3t and 4t, where t is root of 2h by g. So once again, it moves with a constant acceleration of minus g while it's going down. That means the slope of the line is going to be negative and equal to minus g. It's going to be a straight line because v versus t, here the acceleration is constant. So uniform acceleration gives us a straight line of negative slope here, and it starts with zero velocity. So it starts here and it moves with a constant negative slope until it hits the ground. And when it hits the ground, whatever velocity it has, that gets reversed, and now it has a positive velocity. So the velocity jumps to this value. And again, the acceleration due to gravity is negative. So the slope is again negative. So it moves like that. It will be a parallel line. And at 2t, the velocity is 0. That is when it has come back to the starting point. And what does it do now? It continues to move down with the same constant acceleration until it reaches here. And then at 3t, it has reached the lowest point again. And at this point, again, the velocity gets reversed. So it goes up. And from there, again, it moves another parallel line, so forth. So you get a series of parallel lines. That represents the v versus t graph. Please remember, in these problems, while it's moving up, the acceleration is minus g. While it's coming down, the acceleration is minus g. The acceleration, the minus sign tells me the direction of the acceleration. It has nothing to do with speeding up or slowing down. And negative acceleration means a negative slope. So for the entire motion, while it's going down and while it's going up, it's all going to be negative slopes. On the other hand, if you've chosen down as positive, reverse the graph. If you've chosen down as positive, I'll draw it in a different color. It's going to be like that and like that and like that. It'll be these orange colored lines. It'll be the reverse of, that is, reflect the yellow colored lines in the time axis, in the horizontal axis, and you will get, that is changing v to minus v. We are taking down as positive if I do that. But I'm going to stick to up as positive. I hope this is clear. Next problem. This is a very interesting problem. There is an elevator whose cable breaks. It's a freely falling elevator. Someone is inside the elevator, and at the instant that the cable breaks, that is, the elevator starts falling with an initial velocity 0, at that instant, a ball is thrown upward with a velocity of 20 meters per second. Question is, as seen from the elevator frame of reference, that is from this person's frame of reference, what is the velocity versus time graph? Now think about it. In the freely falling frame, that is from the point of view of this person sitting inside the elevator, or rather standing inside the elevator, from her point of view, there is no gravity. The acceleration due to gravity is 0. Every object appears to be moving, every object in free fall appears to be moving with a constant velocity. First point. Second point, at time t equal to 0, the velocity of this ball is 20 meters per second. The elevator's velocity is 0, so with respect to the elevator, the ball's velocity is 20 meters per second. And then, in the elevator's point of view, there is no gravity, so it moves with a constant velocity, so the graph looks like that, a horizontal line. Isn't that interesting? Okay, think about this. This is a very interesting problem. Even when the ball goes up and then starts coming down, even when it's coming down, it appears to have a constant upward positive velocity from the elevator's point of view, because by that time the elevator is moving much faster downwards. So from the elevator's point of view, the ball which is coming down still appears to be moving up. Think about it. That's it for this video. See you in the next video. Bye-bye.